Okay, in this activity, I would like to practice some problems that have to do with conditional probability as well as multiplication probability. If you recall, the conditional probability has this unique notation where we say P of B of A, and it represents the probability that event B will occur, assuming that event A has already occurred. And so event B is dependent upon event A already occurring. Your textbook goes over some information about the manipulating the formula. I want to spend time just going over how to utilize it. So in our first example, we're going to be drawing a card from a standard deck of cards. We're going to find the probability of drawing a queen given that the card is a face card. So that term given is kind of key, that you've got some conditional notation, some conditional probability going on here. Basically, we are narrowing the playing field here. We are going to narrow from 52 standard cards in a standard deck to just 12 because there are the face cards are kings, queens, and jacks. There's 4 suits, so there's going to be 4 of each of those 3 for a total of 12 face cards. That is our narrowed, filtered field there, or filtered total. So we're looking at 4 queens out of 12 face cards, rather than 4 queens out of 52. So you can see that that given really changes your probability quite a bit. Okay, in the next one, we are asked to find the probability of drawing a card less than 8 if all hearts have been removed. Now, I don't see the word given there, but that if all hearts have been removed is another heads up that we've got some conditional probability. So we're going to narrow from 52 playing cards again to actually just 39 when we take all of the hearts, the 13 hearts, and remove them. So we also have 3 remaining suits that have 7 cards that are less than 8. So our numerator is going to be the 3 times these 7 cards for a total of 21 cards that meet that criteria out of the new total of 39. So 21 divided by 39 will give us this probability. In the next component, we're looking at a contingency table. Contingency tables tend to be kind of confusing for students, so I want to spend a little time on these. This one has to do with medical testing. It's summarizing the results for a disease. Positive means that the patient tested as having the disease, while negative means the patient tested as not having the disease. It has nothing to do with a good or a bad outcome. Positive means that the test showed that the disease was present. Negative means that the disease was not present. That's all. Looking at our table, I do want to point out that you want to start out by totaling your row values as well as totaling your column values. The row of the total column should add to 300. The total row should add to 300. You're going to need those totals to accurately calculate your probabilities. Okay, so we need to identify the probability. If a patient is randomly selected, we're going to find the probability that the result is negative. So we are looking at that negative row. In that negative row, we have a total of 144 negative results out of the total of 300. That would be the ratio that we'd use to get that probability. We want to find the probability that the patient is randomly selected and the result is positive. So we can see that we have a total of 156 positive results out of the total of 300. 156 over 300 is how we would calculate that probability. Okay, the next component, the patient, we want to find the probability a randomly selected patient would have the disease and tested positive for the disease. So when we look at this, we're going to be looking at the yes column because they have the disease, and the positive row, we want to know if they tested positive for it. So we have 130 out of the total of 300 tested positive. Now again, we're looking at that overlap here because that word and is implying that the probability needs to meet both criteria. So 130 meets both of those criteria as part of the overlap. The patient has the disease and tested negative for the disease. So this time we're still looking at that yes column, that they had the disease, but we're curious if they have a false negative. So we're looking at that negative row. We have 29 out of 300 met both of that criteria, where they had the disease but tested negative for it. Okay, the probability that a patient does not have the disease and tested positive, we're looking at that no column with the positive row. That would be a false positive. 26 out of 300 had that scenario. Looking for the probability that the patient does not have the disease and tested negative for the disease. So we're looking at the no column and the negative row, and that would be an accurate outcome there. They didn't have the disease and they tested negative, so that would be 115 over 300 is how you would calculate that probability. Okay, so now we're going to be looking at the patient does not have the disease given that the test result is positive. So we're going to be looking at the positive row, but we want to see how many false positives did we have here where the patient really did not have the disease, but they tested positive. And that was 26 out of 156. Now that word given says that we're just looking at that positive row. So out of those positive test results, 26 of them, out of 156 positive test results, 26 were false positives. Okay, so that given tells you that you're narrowing that denominator. Okay, the probability that the patient has the disease given that the test result is negative. So we're going to be looking at the negative row here and looking at how many actually had the disease but tested negative for it. So we've got 29 out of 144. So that's the ratio that you would use to calculate that. So we're looking at, out of the negatives outcomes, 29 of them were false negatives. Okay, the next one, what is the probability that the test provides accurate results? Well, accurate results would be the 130 for testing positive when they had the disease and the 115 for testing negative when they did not have the disease. So we would sum those two, and you can see they are diagonal of each other. So we would sum those two and divide by 300. What is the probability that the test provides inaccurate results? So when we look back at this, looking at the totals again, out of all people taking the test, we had 29 that actually had the disease but tested a false negative, and then we had 26 that did not have the disease but tested a false positive. So these are diagonally from each other. 29 plus 26 divided by 300 is how you would get that probability.